Okay, so let me talk. I'm going to just touch on this. I'm going to come back to the introduction for this later on, but I just want to give you a sense of what this. We're going to talk about this grid a lot, so let me start this idea. I'll just talk through the. We'll come back to it and go through it, but I just want to set this up so it's in your heads. Let me see. So this is this really fantastically, I think a great achievement in the last 10, 15 years of trying to understand systems in general. These are systems that are people-made or naturally made that have, again, these power law size distributions for maybe in this, for lots of things, but in this case, for disasters, right? So this is a very simple little model here of how to make a forest that does a good job with respect to lightning strikes, right? So so the forest is the system. There's some external environmental thing that's attacking the forest, or there's a failure of some sort. You can imagine all sorts of other systems. We'll get back to it, but this is our paradigmatic example is the Death Star, right? So most of the time robust, but you get in the wrong spot or the right spot, depending on whose team you are, and the whole thing explodes. So this is this notion of robust yet fragile. Right? Lots of systems are like this. So this is something, this one is very much like percolation, right? So the idea is this example here, this has got some design and then more increasing design. And so the idea is you have some blank space like this. It's actually all dark, and every white space is a tree. So you come along and you're going to fill your forest in. So you get to design this one. This is not necessarily how things work. It's a little toy model. You get to design this. And in the background is a lightning strike distribution, which is much more concentrated up here. And it has a longer tail out this way, but it's a Gaussian tail, right? So there's no power law stuff in there. It's a Gaussian. It's a little bit tighter this way than it is this way. What you're allowed to do is put down a tree and then run it. Let the lightning strike the whole thing, and then see how much, on average, how much damage you have. Right? How much of the forest on average burnt. And then, so you do that, and then you put down another tree, and you do it again. You put down another tree, and you do it again. And the design differences you go across here is you actually have no choice here. You just randomly put the trees down. So you're just going to randomly put them down. So this is going to work like percolation, because at some point, and for percolation on our square grid, it's a 50-50 thing, right? So once you get to, that's not actually true. I should be careful about that. But once you get to this half filled, roughly, then the trees are going to connect up. There's going to be a giant component of trees. And so, and of course, once you're to 90% or so, there's going to be a huge component. And if you hit that, right, if your lightning strike hits that, then all of it burns. Okay, so here's a case where you have two choices. So to add the next tree, you find a blank space and you add it there, test it, take that tree away, add it to somewhere else, test it. And they're both randomly chosen. So you choose the best location of two randomly chosen tree locations. Here it's going to be D. This is a D squared layout here of a matrix. So now you've got D, right? So 64, 64 by 64. This one you have 64 choices. So you go to each, so you put one down, test it completely, like, it's pretty bad. You strike, you let the lightning run, Thor or whatever. You let the lightning run, burn it all down, put all the trees back, do it again. And you do that for one location until you get some sense of, on average, how bad that is. And then you put it in another location, again, randomly chosen. And for this case, you have 64 choices. And here you choose everywhere. So you always put in the best one, right? You always put in the best one. So you can see that they're very uneven designs. And again, we'll go over this. But they're uneven kind of resulting structures. This is random, no design. It's a random thing. And this is the density of trees that gives you the best yield, in that if lightning strikes this thing, on average, one lightning strike for this one will leave the most number of trees as is possible, right? So we could put it's all black, we put one tree here. Lightning misses it most of the time, so we usually have one tree at the end of each forest fire. But of course, it's only one tree. So we try to add as many trees as we can, until we've connected this enough that just hitting one tree, usually you're losing out. If this is all trees, every lightning strike destroys it, right? So there's an upper limit for sure. This case, you can see there's a little fire break has been made here, and it goes up to here. And there are little pieces broken here. Much clearer fire breaks here. Right? You've got much more design available to you. And as I said, this is the most dangerous place. So you put a little fire break around it, right? It's like when the spaceship is going to blow up, you shut up all the holes get, someone pushes a button, it's very dramatic. This is the idea, is you're closing things off. This is like geometric circuit breakers of sorts, right? So if anything lands in here, it goes boom, it does burn all of it, right? This is a very simple forest fire model. Any lightning strike out here, it's game over, right? But this is the best one. This compares to this one in the sense that this number of trees, this actually will have the best yield afterwards, right? So we could have less trees in here, but in terms of this design process, this is where it got to the maximum yield. After, on average, any lightning strike, even though this could go, it's most likely to happen up here, this is the forest that will have the best yield. And so you could see that you could add one here and add one here. That wouldn't change anything. But if you added a tree to any of this, then suddenly this is all open, right? So you can't add any more. And this is because of randomness. We can't really, do anything more. But you see where we've been able to test it every time, there are no little isolated trees left. But very similar looking thing. So what we're going to argue with this is, some modicum of design in how, or it doesn't have to be design, it could be just, it's a tested system through evolution, bad things happening, can lead to these very interesting, like this is a very low entropy system, right? It's very structured, long way away from this, right? So this is often being used at least as a sort of a simple model for reality, but reality is full of structures like this. So this is highly optimized tolerance is the term here, hot models. So it's highly optimized, and it's mostly tolerant, but when it goes wrong, it has this robust yet fragile thing, right? Out here, really bad, but mostly it's going to go boom and make that noise. All right, so we'll talk a lot more about that in the next lecture, and yeah, okay, all right. Good. So we started talking about this at the, well, let's be honest, I did, right? So on at the end of last semester, lecture. And so we're going to work our way into it again. And it's really thinking about this picture here is the big deal for this story, which is about highly optimized tolerance. As you see, we'll get to some other pieces in here. There's right, highly optimized tolerance. We've got some ridiculousness. There's right, they're not the random forests that you think about in computer science. But so we're going to have this. Talk about self-organized criticality, which is one of these 80s things that's hung around for a long time, but it's got beautiful words in it, right? Sounds really good. So we'll unpack that a little bit. There's a bit of a competition between these two, if you like. Cold theory is there for fun, anyway. But it's a minor extension of hot theory. It exists. It's funny. All right. Most of what we'll do is think about systems like forests, or 2D things or 3D things, where there's a sense that of normal space and things could blow up, but there is a nice extension out into network robustness, which we'll talk about a little. All right, so our motif for this one, I know I have videos, but I'll keep myself under control, is this thing. Mostly solid, but if you poke it in the right place, it explodes, right? So a squirrel bites the wrong line, and the northeast, power goes down. 2003 or 4, you guys weren't born. It was that was the last, I guess it was the last major blackout in the US. I think that's right. I was on the last plane that landed at LaGuardia, actually, and the pilot just wanted to get there, I guess. And we landed and walked through the terminal, which was just no lights on. And then taxis worked, right? So we drove into Manhattan and just silent. It's just, there were cars, but it's just the lights are all gone and no elevators worked. And so it was really, it was people having panic attacks and so on. But people couldn't get home that night. They ended up sleeping in Central Park and stuff like that. It was a messy business. again, New York people were good people. So hot theory. Okay, so here's the story. So most complex systems are prone to exploding in some way. And you know, when you see enough systems after a while, you start to think, well, once things are connected up, that's great. You've enabled something like Facebook, for example, but you become very prepared for the possibility that it will explode, right, in some way that you haven't thought about. So blackouts, disease outbreaks, wildfires, lots of things have spread. We'll talk about disease outbreaks quite a bit when we get to contagion. You know, this is this incredible existential threat, right, that we have hanging over us. It's been around for all of recorded history. Just terrible things come, and we don't really, you know, until recently, we haven't had a sense of how it worked at all. Just, you know, shocking. You know, enormous numbers of casualties. So we still worry about this a lot, and our stories about spreading, you know, really enormous. Those things spread. Okay, so of course things explode, but there's a lot of robustness. This is, you know, infrastructure, right, and maintenance. Maintenance is just not an exciting word, but you know, bridges fall down eventually and stuff like that, right? So somehow, if you're an engineer, somehow you need to make that a more exciting thing for people to invest in and think about. Okay, so maybe a parallel story. So why not? And you know, it doesn't have to be, but this, you know, what comes out of this approach, which in itself as a model is quite reasonable. Whatever comes out, but it does seem to be that parallels too. Okay, so they keep building them anyway, and I don't really want to show you all that. So too much absurdity. Okay, so system robustness, right? So it may result from a number of things. Evolutionary process, right? So it's being tested again and again. There's some uncertainty in the environment, or you know, that you are in competition with your environment in some way. You may be a species, or you know, some sort of ecological sector, whatever it is. So there's that, and of course engineering and design, right? So we can actually, you know, really try to make things that we think aren't going to explode. So let's sort of really fully lean into that. And it's not that evolution produces optimal things necessarily. It produces a lot of very good things, and there are many trade-offs that go into evolution. Engineering, you know, has some similar things. And we saw this a little, you know, how these diverge a little bit with the number of components in systems as a function of size. And, you know, Lego kits was the sort of ridiculous example of engineering kind of departing from what evolution does, right? Which is usually combining many small pieces, right? What are we, 27, 28 atoms, types of atoms? It's not much. It's kind of ridiculous. So, great handle, highly optimized tolerance. Well done. So the hot models, this is the hot theory. This is, and then, so there's that, there's hot. And then there's a more general, so this is a model that we're going to get to. So let me just say more words about this. So it's highly optimized. We have systems that are really good at doing something, right? They're really good at whatever's, you know, their goal. And then there's, they have a tolerance to uncertainty, right? They can handle some uncertainty. But as we'll see, if the world changes dramatically, departs from, you know, in terms of the sort of attacks that can come in or the way things can break, then you can have systems that are really in trouble, right? They can explode hugely. Robust yet fragile is another phrase here. These are good, durable phrases. So mostly good, but can go pop, right? And we have it in myth, right? Achilles couldn't do it all, got the ankles hanging out. River Styx, was it? Or was it a different river? River Styx? Yeah, good. Okay, it worked out pretty well, but yeah, things go wrong. So there's Gene Carlson, he's a famous physicist, geophysicist at UC Santa Barbara. John Doyle. Let's see if I can find Doyle things. Doyle's quite funny. So this is one of his papers. Let's see. This is his first paper, actually, I think. It's a ridiculous character. This is a strong work. Guaranteed margins for whatever this is. Abstract, there are none. That's it. That's the abstract. I kind of want to write a paper one day that just says, see figures 1 through 11, and then it's just, that's it. And it's just all, because in physics you tend to, if that's what you're doing, you tend to put it all in the captions anyway, because people only look at the figures. That's how people read papers, right? They look at the title, and they're like, okay. If they keep going, it's like, let's look at some figures. Maybe the fourth one, backwards, like it's a mess. And then maybe a bit of the abstract, run over to the conclusion. It's completely out of order, right? It's insane. And then eventually, if you're really into it, you'll read it from start to finish. But there's a lot of like, I'm not sure, like, I don't know. Figure 4 is upsetting in its color scheme, like, it's gone, I had a habit, I don't know, this is when newspapers existed, I would just, for some reason, read things backwards. I don't know why I did that, but and I get to the headline and think, good headline, like, just did this. And then one day I realized I was doing. Okay, so that's a quality abstract. There was an abstract like that for the neutrinos of travel faster than the speed of light business, which was a few years ago. Explosion of papers about that. It turns out the measurement was wrong, right? The wrong clocks and general relativity or something. But I think by that point, almost certainly someone had started a financial firm based on neutrinos delivering information. Surely someone had started that. At least registered the domain name, But there was an abstract in there that was, it was like, the question was, do neutrinos travel faster than the speed of light? Question mark. Probably not, was the abstract. Anyway. You've got to have some fun with this madness. Okay, so John Doyle, interesting character. Is he going to pop up? I used to have this fantastic website. It's still pretty good. Anyway, he's a bit of a superhero. At some point, he had the world record for an hour in a human-powered vehicle. One of those like egg things. So he's kind of crazy. Anyway, Doyle. All right, so he's at Caltech, and he loves this stuff. He goes on about it. All right, let's work through these things. So hot systems, right? So there's high performance. They really do something well that you've asked of them, and they're preserved over time. There's some. So this is a nice feature of these models is that we really try to that one tries to put in some uncertainty, right? That there's some environmental attack of some sort, something going wrong. It's stochastic. It's still going to be a toy level kind of thing, but it captures a feature that we expect to see in the real world, or we know we see in the real world. So fragile in the face of unpredicted, right? So it could be that it's within the randomness that you see, right? It's like something happens that is, still within the distribution of possibilities, or it could be that the environment's changed, right? And if the environment changes, then you're in a lot of trouble for these things. So this is, I'll say this again, highly specialized, low entropy configurations, right? So that they really, you can see they have real structure in them. The percolation thing we talked about, for example, right? That was a game where you just you opened up a cell or closed a cell with a coin, right? With the probability P. That's it. So it's a very random, it's true randomness. So you get these random looking structures, and of course I'm trying to think about us psychologically. We see patterns a little bit, even in randomness, right? As we've talked about. But it's a true randomness. Okay, so power law distributions up here. All right, that's, again, this is optional, this is an output. It's not the goal of this. The goal of this was to model systems. Maybe it was, but it was the goal really should be to model systems in this kind of general, useful way. Because we know they have structures, right? Okay. So things we've seen before, variable transformation, right? That was where you could get MIWO, which is mild in, wild out, right? You could have some exponential distribution of some variable. It's got some power law relationship with another variable in the system, and like an inverse power law, and that turned out to give you a power law distribution for that second variable, right? So that was from a little while back. And then constrained optimization, right? So this is the Lagrange multipliers business that we just saw for Mandelbrot. Didn't super work out for that story. It's a nice thing. You can calculate it all. It's all good. But in the end, his exponent's not great. But still, the same kind of principle. There's some quantity that's conserved. There's some constraint, right? Something about it. We'll get to this example for forest fires, but you're trying to maximize something else. Okay. So Lagrange multipliers works. So that means we're going to have this sort of thing. There's going to be a transformation between variables of some sort. Pliplo is bad. No Pliplo. We want miwo. Okay. Mild in, wild out. That feels good, right? Because if we can, explain this mild in one, which is maybe a Gaussian or an exponential, completely okay distributions. We like those. Good. Characteristic size for x, but then y does not. And it's really all bound up in this connection. And if this connection, again, is also reasonable, then we're going to feel good about ourselves. Okay, so this is taken from the original paper. It was set up like this. Here's just an example, probably distribution. And it's just a product. This is a bit of a funny looking thing, but Pij, right? So it's just going to be two Gaussian-like structures. They've got a bit of an offset in them, but two Gaussian-like pieces. So they have, right, e to the, this is, x squared. Obviously, this is decaying like e to the minus x squared or e to the minus y squared. So it's going to be fairly rapid. This is going to be, but these fires are going to be in the corner of this thing. It's going to have something where we have slightly different standard. These are standard deviations, slightly different standard deviations. So you'll see that effect as we look through it. Right. So the idea is we're going to have, and I should probably do it like this. There's going to be sort of if you think about the probability distribution of sparks, it's going to be a Gaussian going this way multiplied by a Gaussian coming down this way. So it really drops off fast, right? E to the minus x squared, depending on these scales. And over here it will be as small as possible. But it's going to be asymmetric. All right, so that's what's underneath all of this. So we're going to spend some time on understanding this thing. How are we doing? All right, so there are 4 examples here, different designs. 1, 2, n, and n squared, right? So 1 means you're always randomly choosing a location to test. That's just part of this, right? So you're always randomly choosing where to put your next tree. The question is, can you choose, how many times can you try that? So with one try, and I'll explain why these densities are different, right? So white means a tree, and black means in effect no tree, but you can see that there are these fire breaks that have appeared. Okay, so let's just focus on A for a start. So D equals 1. So in this case, again, the white spaces are the trees. It's slowly been filling up, and you can see it's very random looking, right? And this is the outcome of a random allocation of trees, because you put a tree down, you run all the fires and do all that sort of stuff. But actually, that's of no information to you because you can't do anything else, right? You've chosen the next location. You don't have anything to compare it with. You're just going to put it there. So that's been filled in randomly. In this case, you've had 2 to choose from, right? So you put in, maybe we're going to put right? You have to choose from the pore space. So we're going to put a tree here. We test it. So make this white, test it. Obviously, any spark in any of this structure, right, will burn. If you put a spark in any of this white space, which is all connected, you see it's connected there. It's actually all of this. So anything that happens outside of this fire break, I think there, burns all of that. So it's not great, right? And this was built out of, just 2 choices. So you're not really exploring much of what's possible. This one is built out of n choices, so this is n by n. So it's a square root of the number of possible locations. Of course, those locations, the possible locations get smaller as you go in, which is a bit of a funny feature. So this one, there's some funny ones here. Obviously, you look at this and you say, well, you could put a tree there, right? And you could put a tree there. But this thing didn't find them, right? Because at this last step, well, I need to explain that properly, but at the last step where it stopped, it didn't choose these as possible ones, right? There are n, in this case it's 64. It chose 64 of these black squares, tested them, and nothing improved. And you can see why that would be, right? Anything you put here, you put a tree in any of this line here, and suddenly you've breached this fire break, right? And it will connect. Anything burning here or here will get all of this. So they're all linear kinds of structures, so you're going to breach any of them with allocating one more. It's true that these pieces are okay. This one, because you'll test everything, it's n squared, you won't add any more at this point. You can't find, right? You will find anything that's isolated. And so you see there are no like double things in here and so on. There's no way to improve this. Okay, so why are these? So there are obviously, there's a lot more white space here. Oh, you know, this is a very thick forest compared to this one, and then this one. All right, let's get some more pieces in here, right? So the underlying distribution for sparks, as I said, it's a Gaussian that falls away quickly this way and less quickly this way. Right, so that's why there's some sort of asymmetry here, right? This is spreading out a little bit because the sparks are not as bunched up. So there's more protection needed this way because the sparks are much more concentrated this way than they are this way. All right, so the game has been that you fill up, right? You run these processes, 1, 2, n, so 64 and then 64 squared. You run them until adding one more tree makes your yield worse. That's why these are stopped at these different points, right? So this is one, and so if the problem you're working on for the square lattice percolation, it's about 57% is the fraction, or sorry, the percentage of filled spaces at which you get a giant component, right? So you can fill half of this up, and then you start to fill up a little bit more than that, and you get to 57%. Adding one more tree here will start, you know, it's finite, but you get to the point where adding one more tree will make will start to connect up a whole batch, right? And then you're in trouble because suddenly the whole thing explodes. You'll see that more as you go along with this percolation thing. But it means that you're well short. I mean, these are almost filled with trees, right? This is a 2D space filled with trees, and there's just some linear structures in here, right? So these are, and that's a big piece here. We have a two-dimensional structure that's been protected by one-dimensional structures. So as we could also go down to one-dimensional structures. So if we have a line and we want to protect things on that line, and we have some attack on that line in some way, then you'd chunk it, right? So whether your attacks are more concentrated, you'd have more fire breaks around that. So imagine just a row of trees. And if there are no attacks out here, then you'd sort of you'd sort of put all your fire breaks over here, right? Your fire breaks are you can think of them as resources, right? This is the way this will get turned around. We can think of them as resources in the sense that they have to be maintained. Even though we're building this thing, if you want to start to think about a more real forest situation, you'd have to create these fire breaks and then maintain them. It's costly. You have finite costs, so the game becomes, you have some cost associated with looking after your system. How do you allocate it so as to best minimize loss? This will then be connected later in the next piece about, and I think this is a really deep connection between how do you allocate hospitals and Starbucks and these sorts of things, right? So that you optimize something about people's experiences, whether it's like the shortest distance to a hospital, on average the distance between people and their nearest hospital is as short as possible, or from a, like a coffee store's point of view, Starbucks point of view, they want as many people in the door. They're not really worried about how far you come from. So they might allocate things differently. There's a flip. We'll get to that, but there's a flip in there that connects this as well. Okay, so optimized forests, they do well on average, right? So they're optimized. And the thing is, this was much lighter weight than this one to create, right? This is a harder thing to do. N squared's a lot. This is a big deal. So you get something that looks very, this is not good, right? I mean, this isn't very structured looking, even though you see the emergence of it just with this 2, and even with randomness, you see that kind of blocking in there. I think, right, there's a fire break around that little block, around that little block, maybe a few. But it is hard for it. It's, it's sort of feeling around the dark a little bit. Rare extreme events will still occur, right? So this probability distribution is, it's non-zero over here, right? It's falling away. It's really concentrated. Most of the, if we think about lightning strikes, and most of the lightning strikes are here in this area, and they're, it's reflecting the underlying attack distribution. But lightning strikes certainly can still happen out here. They're rare, and if they do, huge win for them, right? If you're on the team lightning, it just goes dink. for the greater good, you know, right? So, okay. So that's robustness, fragility. And then look at, let's look, these are connected to the previous page. So, all right, just this one really is the main one. So the idea is, let's take this dotted line here, which goes up like this. This is our randomly filled in one, the design D equals 1 case, right? So we're adding, and density is 1 here, so we're adding one at a time. We don't have any real way to test it if it's better than anything else, so we just add them randomly. And then this is the percolation threshold. We've been adding them randomly, and now we've filled in enough trees that we've started to make a large component. And if we keep doing it, right, so we keep adding trees, which we can do, right? Just keep adding trees, keep adding trees, keep adding trees. Eventually we fill the whole thing up, and then it all burns anyway, but it's pretty bad, you know, it gets pretty bad quickly, right? There's a peak here, and then it's, you know, really drops off. So you've made a giant component of trees, and there are little isolated trees that are separated off that are safe, but eventually you connect to them and everyone gets connected. So we don't just get to the percolation thing and then maybe it keeps going up. You know, I think in the large limit of large N, you know, this really sharpens up because suddenly you've got a big giant component of trees that can burn. So the designless one, right, the mindless one, yeah, is really different to even the design of 2, even the most modest amount of design as well as this goes. Yes?
Do foresters ever use these types of things to like figure out where to put grapes?
You know, there's been a lot of different policies about, I'm sure some of you know more about this than me, and I was going to, there's a podcast I was going to, I think it's 99% design, maybe, forest. There's still just a tremendous amount of argument, actually, about how to do this well. And so there was a push for a long time to stop all fires. Right. So they stopped all fires, like just like put anything out, right? And, you know, it's bad. And what that created, though, was these huge connected spaces, connected you know, forests that had dry material in it, and then the big ones were awful. So you need to let things burn. So that's tricky, right? Yeah. So Australia, they do, you know, it's just like stuff's on fire all the time. So because of Mad Max, or it's underwater. But there's been a real move to saying, all right, go let it burn. So there are controlled burns and all sorts of things. But in terms of, yeah, breaks and so on, oh, I think that's right. There was another piece in there about buildings, the way buildings worked. Codes have changed over time. People have come up with things that seem great, but you know, they've imperiled everyone. Just that I think the materials on houses were incredibly flammable, which you know, obviously makes sense. In Australia, people would build too close to, they would just, because it's beautiful, you're out in the bush, you've got these eucalyptus trees everywhere, which burn like crazy. But they're beautiful, they smell good, right? So you end up with homes just in the middle of trees. The trees are right next to the house and so on, and things explode. Really bad. So let me find that, because I know that tracks some of the political stuff, you know, people being ousted and like, this is a terrible idea. And yeah, bad things happen. Depending on where we finish, I'll show a feel-good thing to do with forest fires. So this is design equals 2. So this one, adding more and more trees has been good actually, right? Because the average forest fire size has been really small. That's what this really shows. This is the yield curve. So yield again is the fraction of the space that's filled by trees minus the average forest fire size. So as it's going up like this, right, this is the overall density. If it's going up linearly like this means that the average forest fire size is 0, basically. Right? Nothing's being reduced off here. But when you get to here, now you have, it's finally become connected enough that you're in trouble, and it's really not going to work out. And so again, that was this thing that didn't look great. Didn't look great, but it was managed to find, you know, that this is a dangerous situation, and accidentally sort of build a wall around it. Not entirely accidentally, but you know, with this sort of limited design, build a wall around this thing So it's going to stop. This is a snapshot of one of these forests that's exactly at this point, right? And the one for design equals 1 is here. That's the density. It only got to 57%. This one is closer to 90%, which is pretty impressive. I should get that back. And then design levels of n and n squared basically look indistinguishable on this graph. They go very close to filling everything up. Because, and again, you're looking after a 2D space with 1D barriers. So they're very thin. You know, I mean, obviously, a large enough scale, they'll be incredibly thin. But they require, if we think about maintenance in some way of this being actually about a real forest, then there's cost to maintaining them, and that's why we could build forest breaks everywhere. We could make tiny little patches. Then you have problems with ecology, right? You know, whatever animals need to, be able to have a big enough range and so on. So that might be problematic as well. And then again, some plants need the burning thing, which is messed up. Evolution is just messed up. Okay. Evolution needs some sort of avatar. I know there's the blind watchmaker, but it doesn't really sell like Santa Claus, right? You need some charismatic anthropomorphism, right? What's that?
So not primordial.
Yeah, see, maybe it wins. But Dawkins is the blind watchmaker, which, I guess also knows as a watch, so that's cheating. Okay, and this one is for, this is a different one. This is for really small n's, which is kind of hilarious. So this is n equals 2. This is a 2 by 2 with trees in it. I don't know how they even, it just seems ridiculous. Anyway, 2 squared to 2, that might be a mistake. 2 squared up to 2 to the 7. So this is a thing where we're building up and design equals 2. Yes, right. So this is a design equals 2 case. This is what happens as you grow the lattice, as you make a bigger and bigger forest. This is a finite story, right? So what's the effect of making the lattice bigger? And you can see it's approaching some limiting thing here. I know I really need that in this course. There's a lot you can do with running a simulation on some size lattice and then increasing it, and then seeing how things scale. It's a very natural question. But this suggests that it actually is approaching something, right? That there's some, and this is for the d equals 2 one, that it's approaching something that's just a bit over 90%, and that's a sort of a real limiting case. Analytically, that would be probably impossible to work out. It's a bit of a stylized model. Okay, so some of this is a bit funny to look at, but it's worth, you'll see if you can reproduce these. So some ridiculous graphs. So this is the cumulative probability. So this is what we call a complementary cumulative probability distribution. People have different names for some of these things. So this is the distribution of forest fires at that peak density, right? So if you run it, or you test this thing, this is the distribution. Not really super power lawy, but that's what they're trying to claim there. And certainly you get it out analytically. This is a small example, 64 by 64. And then this is, well, d equals n squared and n equals 64 at equal density increments. So this is a, okay, so this is a very interesting one. So this is the super designed one, right? Over here, this is the super designed one. And right, so d equals n squared. It's for 64 by 64 again. And then the idea is, as you go up through here, right, from bottom, this is when the density is at 0.1, 0.2, 0.3, 0.4, 5, 6, 7, 8, 9. So what this suggests is that, and it's not bad, I guess the colors go back and forth. And this is a ridiculous scale here, right? This is 20 orders of magnitude here, so it's all compressed. The idea is to, what they're claiming to show here is that as this thing is being built in this super design version, right? So we're just looking at this close to 100% filled version, but it's being filled in. It didn't look like this ever, but it's being filled in. It's sort of finding this structure slowly, and it'll be interesting to look at that over time. I should have that. Yeah. Okay. Yep. As this is, so I don't have a plot of this, but as this is filling in, it's creating structures pretty quickly. It's finding this shape pretty quickly. And then when you test it, the claim of this graph is that even when it's only 10% filled and up to 9% filled, it's still got these power law size distributions for fires. So this is away from the best yield point. So this is a very important thing, right? So the stuff we've looked at up until this point has been about, we're designing these forests, and we get to the best ones, and then show, what they look like. But actually, in this whole build process, there are these power law size distributions for these forest fires all the way along. So it doesn't have to be tuned to be that. As long as there's some, whatever the density is, there's some sort of process that's acting on this system to iteratively, over evolution perhaps, or some sort of clever engineers, make it more safe, then you're going to end up with these uneven distributions, which is all very good. It's just that terrible things can happen, right? So this is super well designed. It looks, it's very non-random, right? This is a low entropy, what we call a low entropy state, right? You can't, if you reach into the bag of all n by 64 by 64 matrices where you've put ones in them, right? You've put, say, 98, filled up whatever 95% of them with ones. You've just thrown ones down. Right? So random matrices is a whole huge deal that people think about for all sorts of reasons. But if you threw all those things down, you would never get this one, right? It's in the bag, right? This bag contains all possible random matrices with this many ones and this many zeros in it. Just you would never pick that one out. You would always pick out things that look like this, right? We'll see that later for networks too. The big bag of networks that I have to say this over and over. It only contains, or it seems to only contain networks where the number of friends that each node has conforms to a Poisson distribution. These are Edish-Rennie distributions, networks, I should say. Pure random networks. Trouble is, they don't exist in the real world, right? No one has ever seen one in the real world. Lots of networks have been looked at now. There are just none. It's just in the big bag of random networks that if you keep reaching in and pulling them out, right? So every network that has 10,000 nodes and say 20,000 edges, you've got that bag. It says n equals 10,000 and m equals 20,000 on the side, right? So it's a huge thing, right? Combinatorial explosion. Everyone you pull out has this Poisson degree distribution. But in there, and so you never see them in the real world. But in there are real world ones, right? Because you've allowed every possible one. It's just that you never find them this way because they're grown, right? They become things. And so pure mathematics and combinatorics were playing around with this stuff, which was super fun for like 50 years. And all these people who didn't live in houses like Edish, for example. If you know this guy, right? He's just shipped around the world from place to place. Never allowed to drive a car. He was on speed the whole time, which was interesting. Worth reading about if you don't know about Paul Edish, one of our Hungarian greats. He went off speed for a while because of some bet or something about his health, and then only lasted a month, and he came back saying mathematics has been harmed because he was really out there, called children epsilons and stuff like that. Anyway, so, which is all good, right? I mean, well, maybe not that bit, but I mean, it's fine to think about pure math and so on. It's just that in this is a good example of like, the universe didn't produce any of those, right? And so those things only exist in people's brains, which are very creative things. But, okay, so this is a similar sort of story. You're never going to get this by just randomly sort of shuffling around, right? It has to be made by engineers or beavers or whatever, things that have plans, which turns out to be also evolution over a long period of time. Okay. So, pretty interesting, right? So, when we get to, I'll come back to self-organized criticality, we'll come to that in a little bit. this is very much against self-organized criticality, which expresses the idea that there's just this one critical sort of structure of the system or a critical point that somehow nature or natural systems or whatever it is pushing towards that point. So this is a big deal. That this building, growing process could produce these power law size distributions roughly independent of the density of it. That's kind of huge. Okay, this could be ridiculous.
Luke, at that speed, would you be able to pull out in time?
It's just like Beggar's Canyon back home.
Use the Force, Luke. Let go, Luke.
The Force is strong, let us win.
Luke, trust me.
Lost our cue.
The Death Star has cleared the planet. The Death Star has cleared the planet.
Rebel base in range.
You may fire when ready.
Commence primary ignition.
I have you now. What?
Yahoo! Look out! You're all clear, kid. Now let's blow this thing and go home. Stand by. Stand by.
Payoff is this.
Great shot, kid. That was 1 in a million.
Remember, the Force will be with you, always.
Hilarious. So the 1 in a million thing is the key bit at the end, right? So that's how stories work, right? 1 in 100. You're not going to write a story about it. So it's often going to be framed that way. So we do stories badly in various ways. I mean, they basically help us get through life, but there are some things that we do that are really wrong, and that's one of them, which is we really like that. Because if there's a 1 in a million chance that the hero wins with 100% chance. Right? It's really magnificent. Anyway, so I know that was a bit long, but that bit at the end is just fantastic. There's actually in one of the Pratchett books from the Discworld, which if you've read, there's one bit where there's a couple of idiots who are conspiring to make their chances more like a 1 in a million, so that then they'll win. It's not dangerous enough, so they like blindfold themselves and stuff. Yeah. Okay, so this is just to sort of say where we've gone with this. So d = 1 is percolation, right? Just to remind you about that. Randomly adding trees, and so here's some extra pieces. Below this critical density, no fires take off. This was about 0.57 in this case. Or, very small ones, right? There's some like logarithmic thing there. And above it, you've got a percolating cluster of trees. You're in bad shape. You've got a chance that it will, be hit every time. It's built independent of that underlying distribution, right? So the fact that the lightning is more up in this corner, this system has no idea about that. But has a good chance, certainly as it gets further above this critical threshold, of creating a cluster that connects into that corner or gets close to that corner is a lot of trouble. So there's really so here's the big piece here, and you have this in your assignments now. So theoretically, only at that threshold is when you have a power law size distribution of forest fires. So it's really truncated below the threshold. And as you get to the threshold, it starts to kind of move out and out and out until you get a power law. And then what you start to get on the other side is lots of small forest fires again, but then just this big spike of a huge one. Because there's this big giant component and all these little ones, right? So you can have all these little forest fires or a monstrous one. So as you move through that threshold, there's only that one point where you get this power law size distribution. Randomness, featureless. Forests are random and featureless. Hot, on the other hand, power law distribution, it doesn't really matter, right? There's a lot of variability. You can have different densities below, certainly away from the percolation threshold, and for this kind of system, for a square grid system. There's no specialness of a critical threshold. So it's moved away, it's lifted that problem away, because that was weird. Most of the states are okay, and it's not bad if the uncertainty is well characterized. It's still, you could have these giant things explode, right? That's really bad. But if it's well characterized, it's kind of okay. We can handle some of this uncertainty. But if this is characterized poorly or it changes, right, the environment changes, then failures become, and you don't adapt, then you get into more and more trouble. So that's an extra level of like how fast you can adapt these things. All right, so that's kind of what I want you to know today. And I'm sure you've seen this, but there's going to be an ad. There's going to be an ad. No. This guy, what a champion. He's worried about this bunny. I don't know who. Then people argued about who this person was. Someone apparently said, that was me. And then someone else said, no, it was me. Humans, right? So they do this thing. Look at this. It's going to get a rabbit. Dude is a total hero. I think he ended up on Ellen, like everything, like, right? Right? But then there was a fight about who it was. This other guy's family is saying, no, it was our kid. And they're like, no. That's to make you feel better about the world. Okay, so we'll be back on Thursday. We'll talk more about HOT, and then we'll start talking about supply networks. Thank you. Let's get back to robustness. I keep destroying things. Okay, shouldn't have done that. There isn't too much to add here. Just a few sections, and so this was the end that we got to last time, which is that we have this contrast between a d = 1 random forest, no design situation where trees are being thrown down randomly, just to sort of get us back in the frame here. And there's really only this critical density where we have these power law size distributions of forest fires, and above it, everything explodes. Of course, it's a phase transition sort of story, but you get a giant component, and below it you don't have anything like that, and that's a real transition, a real change in stark contrast, I should say, to the HOT model, where there isn't a critical threshold or critical density of trees. You can have lots of densities of trees that have power law size distributions of forest or subforests in this case. And it's a very structured thing. It doesn't, it's very low entropy. And if it's but if it withstands some attack or some assault from the environment, but if that gets characterized poorly, then, or changes, the environment changes, then you get into trouble. Okay, so we don't have to talk about this too much, but this is a bit of a funny, so in some ways this is terrible, right? Like, where is it? This is really a complementary cumulative distribution function, right? That's what we've framed as p greater than or equal to. Try to be very consistent with that. And then in here somewhere they have like a calligraphic p L greater than or equal to Li, so just no one cares. Anyway, that makes this a little hard to look at, and we don't even know, right, if this is log 10 or whatever. But this is looking at different things, and this is starting to look at some linear. So there are forest fires in here. These are forest fires. There's also things like packets on the web. So you can think of that as a one-dimensional piece that's being broken up in some way. Now, whether that's a robustness story, not sure. Okay, base, we're upset about that. Okay, so let's set up just the abstract calculation here, and you can work on this. It does use the Lagrange multiplier stuff. It's not as maybe out of control as that Mandelbrot one. But the idea is going to be this, that we're going to have some failure size, right? So this is our forest fire. This is now abstracting a little bit. There's some resource, which for us is, for the forest analogy, is going to be the fire breaks. And when we think about resource there, we think about the maintenance, or, there's creation of them, but then the maintenance of it, right? So there's time and money, or whatever however you want to measure it, that goes into preserving these breaks, these fire breaks. and that there's some connection between them. And so we'll see why that makes sense. We want to minimize the forest fire sizes. That's the idea. And there's going to be some constraint on the resources. Right? There's only so many fire breaks we can put in. And so the cost is going to be what's the probability of whatever it is that explodes times the size, or whatever that weight of explosion is. And we're going to go across all these sites. So that's the idea, right? And there's going to be some constraint. All right. So we'll just set this up. This is a bit funny how you can do this, I suppose. This is cost save of fire. And we're looking at all these sites on a grid. This is the probability that the ith site, and you'll do the simulation, gets a lightning strike, and then that's the area that's connected to it. Yeah. Right, it's part of some subforest or a forest that has some area. So every time it hits, it goes boom. And we're going to sum over all of them. So there's a little probability that's attached to every, so we've got some area. We're really essentially adding up all of the probability that lightning hits inside that area. That's going to come through there. There's a constraint. So how do we put in the constraint? And this is maybe where you'll see when we get to supply networks that there's a connection here. So we're going to sum again over all the sites. And the idea is that we've got some region, some area around it. Right, there's some subforest. It's got some fire break around it, and the fire break's length is going to be proportional to area to a half, and that's just a simple scaling thing. It's a dimensional analysis piece, right? So this is just saying like we have a square of area A, then a typical size, the width of that square or the length of that square is length. Is a to the half, or if the square is length squared, we will have length here. But since we're dealing with area, we're going to take the square root of it to get a sense of what a typical size of it, and that gives us an estimate of the circumference as well, at least proportional to. Now, every site in that area is going to contribute, so we're going to divide by the area of it to kind of get a normalization. So when we sum over the whole thing, we'll get the cost of the firewalls. So we're assuming isometry, that there's nothing funny in the shape, right? So that's the scaling here, that this is a nice scaling. And if we go up to d dimensions, or we go back to, say, 1 or 3 or 4, then this half is going to be replaced by the scaling. All right. So that's a question, and you can work through this, and you get, and it doesn't take too much work. You get the area, the probability of a forest fire of a certain area is going to scale as area to the minus gamma. So we get a parallel size distribution. Boom, boom. Exciting. Okay. But again, this is an optimality argument. This is different to what's happening over here, which is of course we're creating this thing, right? So this was this little greedy algorithm to kind of make something. I was going to say that it would be hard to go the other way, fill it up with, at least from this kind of toy model, fill it up with trees and then start to make fire breaks iteratively, right? Because your first one wouldn't do anything, and then the next one wouldn't. It would be hard to find these breaks starting from, at least using this algorithm. I mean, we could see it, but using this kind of incremental algorithm of removing one tree at a time. There's a continuum version. I'll just sort of set this up. So there's a cost function. We're integrating over some space. There's some cost at each space. If it gets hit. So we have some point in space. This is the probability, okay, that an Ewok jabs something, right, and it goes boom. Lots of systems explode. And so there's some constraint as well. So this is sort of, so this is in direct analogy to a couple of slides back, or the previous slide. There's some resource. Yeah. And then this, whether this is true or not, right, so you have to have, this is really the big thing that makes it work, that there is a relationship that's an inverse parallel between the resources and how much damage is done if that particular region is hit. Okay, all right. So I'll show you a couple more things. I'm not going to show that. Okay, let's talk about self-organized criticality, because this is sort of a competing older theorem. There's a Bohr-Hayes reference for no apparent reason. But let me explain. This is a very famous paper in the 80s. And I'm just going to use this picture here. I think I'll do this. So the observation was, granular matter is really complicated and weird, and it matters tremendously, right? I mean, just landscapes, where we put houses and how things kind of function like that. Our food, rice, wheat, all these things, we're sending all the stuff around, we're putting it in containers. I'm sure you've made a mess of things where all the salts come out at once or something because the lid came off, or your cereal exploded. Because cereal's pretty weird, right? If you've got little, whatever, things get stuck together and it might not come out, right? So granular media can flow like a fluid sometimes, and then not, right? And I've talked about it a little bit. So it's something that's been studied pretty more, I guess, starting in the 80s and 90s. It became a thing that was more studiable. You certainly need computational power there as well. But again, huge thing, matters a lot. So there was an observation, of course you start to make simple experiments, right? So just to see if we understand anything. And one was a sand pile model. So we're going to drop grains of sand, and if you want the idealized one grain of sand at a time, makes a little sand pile, right? And so this is just importantly, I guess, it's falling onto a 2D plate, so you're getting this little cone that's building up. And then what's called in geomorphology, angle of repose gets reached at some point, and that's it, right? It has to, it's too steep and there's avalanching. So the story with this was sort of yet another example of something where you get power law size distributions and could be a toy model for financial collapse, right? People got a little out of control here. But so you would get, now and then this would just sort of bounce down, there's one, whatever, and then now and then you get a huge one. And so the idea was, we're getting power law size distributions. Can we understand this with a simple model? And, okay, so there are a couple of levels here. First of all, the simple model that became very famous and is behind what's called self-organized criticality. And the self-organized part here is it's a driven system. Things are coming in all the time. It's being driven. And it starts off with nothing. It gets to a state that's on this edge of criticality. Like it's always going to be in this power law size distribution state, right? It's never going to collapse back to zero. It's never going to be a long way away from it. It's never going to get really tall. It's always going to be in this somewhat precarious state. So here's the model, and it takes a long, if you read the paper, you don't think they're doing this, but just make a grid like we have underneath this thing, just make a 2D grid, and then just rain down these little blocks, right? So it's sort of a weird Minecraft thing, I suppose. You rain down these little blocks, and the rule is once you get to 3 blocks and you add one more, then it's going to go boink and spread like this, right? And it doesn't matter what's in the neighborhood. So if there's a tower of 3 blocks here next to it, this block will just go on top. And it's just a very artificial model. It's just going to happen. But of course, now that one has 4, and so that gets to go spoink as well. So you get these little, maybe a small thing, and now and then a bigger one, and so on and so on. You get these avalanches, but they're sort of these spreading failures. Okay, so this is kind of, when you step back from it, it doesn't look like this at all, right? It's not even, so this is supposed to be a model of other things, like financial collapses or whatever. This is not even really close to that, even visually, right? This is like some sort of thing happening at carpet scale, like spreading like that. It has no height to it. It never gets above 4. And then it also turned out that sand piles don't do this. They don't have these, like the early experiments or whatever was going on. People really got into this. This is a great, simple example. Can we understand this thing? People started to do it over and over again and couldn't reproduce or produce these power law size distributions. So there's a lot of fighting. I was once on, a long time ago, I went to this NATO conference on Corsica, which had all these engineers and physicists together talking about granular media. And the engineers were really upset with the physicists who were just doing crazy things. They were just like throwing away momentum. We don't need that. We'll just make a fun toy model. And they're like, you monsters. And a huge argument, I remember that, was what's the pressure distribution like underneath this? And so there was this idea that actually it kind of has this, I guess the best way to do it is to say like this. It has a dip in the middle. Like there's less pressure in the middle. And I know I talked about barns and circular barns the other day and that sort of thing. This is really a feature of granular media. If you fill up containers, then it starts to have so-called force chains where this grain is resting on this grain, is resting on this grain. It doesn't just push down. It starts to go out, kind of almost like lightning structures. There's some branching structure to it. And then they come together and maybe end up pushing on a wall. So it isn't clear like how so-called force chains go through these things. Anyway, a lot of argument about that too, and I'm not sure what's been sorted out, to be honest. But the idea that there's a dip in pressure. All right, so self-organized criticality, a bit of a funny thing. Quite famous, often invoked to explain these behaviors of real systems, but with a very odd toy model. I mean, I've showed you a range of toy models by this point. I think some of them capture reality in a much better way, like Rich Get Richer is a great, fantastic toy model, which has some sort of surprisingly strong connections in terms of actual quantitative measurement with real world. Ising model is pretty good. So the idea is, and we could see it with this sand pile, that it would stay at this kind of critical state because it's kind of driven. If you want to take an icing model, this is a little magnet thing, you'd somehow have to get that temperature of right at the critical point, just before a lot of them start to line up and be on the same team and away from the other side where they're jumbling around because it's too hot for them. So there's this idea that somehow there's feedback and it isn't being driven or controlled. I think someone did show that this so-called sand pile model of Purbach and his colleagues was the end point of some other model, right? Like you could see that it was like the zero temperature state of some other model. So it wasn't like it was being tuned in some way. Okay, so it's Bach, Teng, and Weisenfeld, famous paper, 87. I kind of want to look at that one. So the problem is the critical state is a very, very specific point. You have to be there somehow. You have to always be at the edge between ice and water somehow. Somehow the system, somehow these more complicated things that are not necessarily physical systems. So self-tuning is not always possible, right? That's absolutely true. Lots and lots of arguing. Had a good brand for it, Sock. So that was good work with Hart. You had to have a thing to fight it, at least verbally, which we'll talk about more. Let me Purbach, Google Scholar. Purbach tragically died young. So this has been created in afterwards. There you go, 8,000 citations. Pretty solid. You'll see when we talk about complex networks, those fields which start in the end of the 90s, I'll tell you a lot about them. The citation numbers for them are more like 40 to 50,000, which is an indication that you got other people excited. Of course, billions of people can be wrong, but it does in that case mean you've done something. Okay, so Purbach has this great book from years ago, which I guess if one way, How Nature Works, right? So awesome. So he was famous for being, I met him once years ago at Santa Fe. He's a lovely guy, but I guess in conferences, really, just would go at people, just not pleasant, which, is some people's thing. I don't know, and so in Australian rules football, there's a thing called white line fever, which is nice people off the field, nice bloke, but when they cross the line onto the field, they're a psychotic nut job, which somehow is okay. Anyway, but video means some people end up in jail. So this is it. So he writes this book, right? I understand everything. A little strong, perhaps, but good for him. He had fun. Anyway, so as I said, the sand pile thing didn't really work out. So we've got this great analogy for stuff. Turns out that little model, which is eminently sort of makeable, I suppose, and testable, doesn't produce these things. So humans, are very determined, right? So they keep exploring. What this is a snapshot from two plexiglass plates put together, and this is long grain rice. Doesn't work for short grain rice. Long grain rice being dropped in up here by the graduate student. So there's a graduate student here. I'm sort of saying this hypothetically, but I'm pretty sure, who's like titrating long grain rice, which they sourced at a local store. And then there's another graduate student here counting the sizes of things. Could be the same one, but professors are nasty people. So and you could imagine maybe 30 concurrent experiments with different kinds of shapes of things. Yeah, rice, couscous. Let's try some teff today, poppy seeds. So it turned out that having some elongated structure, like in this case long-grade rice, produced the avalanches. This is still debated about, but it was something that finally we made this thing, which we think is a thing that models other things, look like the thing we believed it was. Yeah. Sheer determination.
0.049.
I don't know. I should. These are. I think it was a Norwegian group. I remember seeing them give talks about it and people yelling and shouting and being upset. I know. Sand piles. All right. So, but I have to tell you, this is a whole cornerstone of thinking about huge systems was sand piles. And I was sort of surprised a few years ago. I was traveling, meeting some people at I think it was Utah, just talking to people, as you do when you kind of travel to give a talk, individual talks. And there was one guy who was working on what he called sand pile things, and so it was on networks, very abstracted by this point, but it was exactly, you can imagine the network version of this, right? So you have your little beans at each thing and then spreading. And you can see it feels like it's kind of like diffusion. But as far as I could tell, I didn't know about the original work at all. Like it had just sort of marched off into, degrees of separation, and the original sort of work had been forgotten, and now it's this fun, abstract, pure math thing with ideally no application, right? Unsullied by potential to be involved in reality. Maybe it will, in generations to come, but that's not why you do it. That's okay. Anyway, so it lingers. So hot versus soft. So this is Doyle and Carlson again. So they have this, again, a sequence of stuff about hot, highly optimized tolerance. And maybe you can see up here, this is another, this is yet another version, different kinds of things up here. But they sort of set this up. This is a PNAS article, so this was sort of a reasonably big deal. Hot versus suck, right? They're both getting these power laws out. Hot has a better story for its optimization. Doesn't have to be that, this is just a toy version of it, but this idea of a system being tested and refined in some way and producing better versions versus some kind of self-tuning. You also see this, you'll see the term edge of chaos, right? That's another beautiful framing, and it's the idea that you're kind of like this sandpath thing, that somehow the system is on the edge between maintaining structure and on the other side, like mutating too much. And you want to have some balance there, obviously, right? Rocks are pretty good at maintaining structure, but they don't produce iPhones. I guess we make them out of rocks. So anyway, so this was a big deal, which I hope I've got across, which is that you could have many different densities, so there's sort of potentially a power law size distribution, although it's not this kind of a absurd looking thing, but they're different densities at least. Yeah, SOC ones have a special density, right? It's the percolating threshold sort of thing. These produce very specialized structures. These are random structures, the generic randomized structures, so low entropy versus high entropy. So they're quite different in what they make. And I think people years ago would have a lot of success just saying, hey, I got a power law out. We'll see that with complex networks, with scale-free networks. Just getting a network to have a scale-free, a power law size distribution for numbers of friends that nodes have in the network was an achievement, no matter how wildly off the exponent was, right? So it was clearly not a match, but it was enough to say, I've got the shape of it. I didn't produce a Gaussian, like I produced a power law, and that's what I see. We don't have to go through this, but this is sort of then a table that summarizes a lot of things we just talked about. Yep. Okay, I think that's good. Okay, so cold theory, great question the other day was that led to this. So it's I realize I didn't remember the word constraint. Constrained optimization with limited deviations. Well done. So we've got hot. Let's make a cold model. And let's make, it's not just for fun. It's actually a little bit more serious than that. It has a nice, it has an important extra step in here. So we're going to just kind of punish or depending on how it's created or whatever, tested, we're going to sort of we're going to be worried about large ones, right? We're going to weight them a little more heavily. So we're going to sort of simply punish the evolution algorithm not punish, but we're going to make it favor moving away from any large thing. So what that does mean, as I said the other day, this is going to mean the average forest fire, for example, for the forest fire example, is going to be larger, but you'll never get a gigantic one. So it takes away the chance of catastrophe. Okay, that's a Mark Newman paper. We're going to talk about Mark a fair bit. Yeah, so what you end up with, do I have it? Yes. This is the sort of thing you, and maybe I haven't said this enough. This is a very typical kind of form that you get out of a lot of systems. There's a power law decay and then an exponential. So a product of a power and an exponential. You see that very explicitly. It's a different kind of thing, but for gamma distributions, this is a positive thing and then exponential. This may not, you might think, I think when I first saw this, I thought, well, this is sort of the dominant piece in here, right? This exponential, that should just kind of crush this thing. But if this XC is very, very large, right, 10 bazillion, then, and your X is starting, it's sort of order 1, it takes a long time for this exponential, even though it's an exponential and it goes like this, it takes a very long time for it to start to kind of really get into its decay. So if this is very, very large, then it's going to take a long time. And then when X is of that order, when it's similar to X sub C, this starts to dominate and then it dies. And so on a log-log plot, what you see is this thing with a nice gamma, right, minus gamma, it's going to have this power law and then go and fall off. And where it falls off is around here. So the framing for this is exactly, it's power law size distributions with an exponential cutoff. That's what that means, an exponential cutoff. So in our assignments, we've just sort of said, there's a beginning and end, there's this a smaller scale and a larger scale, and it's a pure power law in between. This is a much more common kind of structure, and it comes out of theory and it fits observational stuff. So good thing to know. And there are other pieces I said. So Weibull distribution, so it could be this sort of thing. The Weibull distribution is a special little character where when you've got the right exponent, it collapses back to being, right? So when gamma is 1, which is a funny sort of thing, it's not going to work out. It would clap, I'm saying the wrong thing. Yeah, when gamma is 0, then this is e to the minus x, right? So it has the exponential as a special case in there, and then can vary around. Okay, so we're going to talk about this later on when we get to networks, but it's error and attack for complex networks, so it's sort of another part of robustness. This is early work, this is 2000, but and then we'll talk about contagion and so on. So we'll see some really, I think, kind of shocking stuff really for threshold models of social contagion where everything looks like it's fine, but if it gets hit in the wrong place, the wrong person in a sense starts things off, or the wrong small group of insignificant characters kind of start the wrong thing off, the whole thing can explode. So, which is very important to kind of understand, like, how do you get these massive transitions in society that, have happened in the past? We've got all this historical evidence. How do those things happen? Okay, I'm not going to show you that. All right, so it's Robot Chicken where the emperor falls apart mentally. Anyway, so it's probably a little too much. You can enjoy that your own time. Okay. But this robust yet fragile thing, we put into stories all the time. I had the 1 in a million thing the other day, Smaug, Tolkien, right? There's one scale, there's always, that's always like, there's one button you have to reach and it turns everything off. It's a convenient thing. But it's also, in Achilles, we mentioned that as well, but it's also actually true of some real systems. A squirrel eats the wrong bit of a power grid and it all explodes. All right. All right, so a forest fire example, here it is. So we're going to set up an n by n grid. This is something you guys will code up. Sites are going to, there's going to be some density to the thing, but we're going to figure out a way to reallocate it, not in a random way, but there's an overall density, right? So it goes from 0, no trees, to 1 where every site has a tree. So therefore, same thing. So if we just bin all the, we take all the sites and count up all of them and so on, that's fine. But there's going to be structure in here as well. Okay. So we need to figure out how to allocate them. And from a, if you say, oh, you can fill up half of this forest with trees, and how do you want to do it in an optimal way? That's a huge combinatorial problem, right? You can't enumerate them all and say, test them all. So we're going to have a strategy to get around that. But in principle, that's what you'd want to do. Let's try every possible forest. But you have to get there. You have to grow it some way, so that sort of makes sense. You'll see it's very stylized, not how forests work kind of thing, but it has this growth aspect to it. Or at least a testing evolutionary aspect, let's say it like that. So fire's going to start at some location. We've got ij, right? According to some distribution, pij. So here's our environmental attack, right? We've got a forest, trees that are next to each other. If a tree burns, then the trees next to it burn, just adjacent, right? Just the 4 adjacent trees. You can put on lattices, whatever you want, put on other lattices or think about other kinds of connections. But that's just a very simple game here, right? So tree burns, and then any trees on the adjacent lattice points will also burn, and then that will continue. And you don't have to run that process. You just have to know this tree is part of this cluster. Any tree that burns in there, that's off, right? So you want to do a thing where you find all the cluster sizes, then basically you're going to turn your computer into a rampant arsonist, right? It's going to just light up this forest over and over again. It's going to be kind of messed up. You're going to put the forest back together and then light it up again, and then do it again, and do it again, and do it again. All right. But each time you do it, you're going to choose a site based on some underlying probability distribution. So our pyromaniacs will kind of have some uneven distribution in where they are. That's really where this starts, right? So if it's an even distribution, you have no idea where the attack will come from, then you might as well just put your trees down randomly, right? There's no great way to, you don't want to bunch them up on one side versus another side, because, right, it's completely uniform. So fires are spread from tree to tree. And right, as I said, connected clusters will burn, so you don't have to run the simulation. You just go count up. Empty sites will block fire, and so here's the idea. Here's the little game you want to play. You're handed this. You're told the grid is whatever it is, 64 by 64. It takes a while to do this, and it's kind of impressive. This paper's from the end of the 90s, actually, when the first paper, it's a whole sequence, that they were able to do some of this computationally back at the time on a Pentium 3 or whatever was the thing. Okay, so here's what we want. We're going to build fire breaks, and the fire breaks will just be these empty cells. So essentially, we're going to build a forest with fire breaks to maximize the number of trees left on average, right? So we're going to build our forest. It's going to have a density, say, of 75%. We're going to put them all down, and then we're going to test over and over again with this. Right? We're going to say light, 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 light. And on average, we'll get an on average number of trees burnt. Sometimes they'll be bad, right? They might burn a whole lot, but on average, if it's not too bad, then we're fairly happy with it. And then you set up another forest, and you set up another forest, and you set up another forest, and then test and test and test. So if let's say this is the grid, if all of the sparks are in this corner, whatever, there's just some kid here things have gone wrong, and they're just they want to light up trees, and they can't move for some reason, then you fill this whole thing up with trees, right? And there'd be just this little barrier around here. This would be a little place here, right? And so that'd be fantastic, right? Every time this lights up, nothing burns. And so you've got this, on average, your size of your fire is 0. So that's how you would eventually find that. You'd add trees and eventually you get that. But if there's some distribution that's coming out like this, then maybe you want to put a lot of trees over there to start with, right? Maybe it's more concentrated. The lightning strikes are concentrated over here, but kind of have some distribution going out this way. Yeah, then you want to fill up over here and then come in this way, come in this way, come in this way. But you want to sort of build a fire break around this, right? And then the question is, what are all these little patches like in terms of size, in terms of area? So here's the example. And so here's the way to get around this horrible problem of like how would you enumerate all possible forests, right? We can't do that. Makes funny noises. We can't do that. So we're going to do like sort of a greedy approach, right? Computer scientists love this sort of thing. Love proving in incredible, excruciating detail that it works really well. But this is just here's a little ad hoc way of doing it. So we're going to add this thing now, a design parameter, which is going to be how many times you can test adding a tree. So you've got your current forest, and you add one tree to it, test it by letting all these lightning strikes go. So a lightning strike goes, see how much is burnt, put it all back together, another lightning strike, burn it again. And the way to do this is you actually allow you go through and test every possible cell. You say a lightning strike here, lightning strike here, lightning strike here, and then you can multiply it by the probability there was a lightning strike there. So you don't have to do sort of like one at a time, like one actual lightning strike. You can go through all possible cells and say, here's a lightning strike, burns this much, put that forest back together. Here's a lightning strike, burns this much, put the forest back together. So you can actually go through all of the initial points and then weight them by their probability of happening in the first place. So that's nice. So it feels like you can get a very thorough way of doing it. But here's the extra detail now. You're allowed to test D new locations for a tree. So you've got your forest, it's laying out, then maybe there's a space here. You randomly choose that space to add a tree to. You put the tree in, now test it. Let's say D equals 2. You test it completely, you get the average forest fire for adding a tree there. Then you take it away, and then you randomly choose another open space. So it's here, you put a tree there, and you test it all again. And then you take the best of those two. Look.
When you said weight them by the probability that they would burn, is that going to be uneven based on the distribution?
Yes. So if it's even, and you could run the simulation, if it's even, then you shouldn't really get any particular structure in it'll try, but you shouldn't get much structure there. And it's going to be bad. Yeah, it's going to be bad. That's, and we fear randomness for good reason, right? It's just, there's no way we can cope with it. It's true we go to casinos and lose all our money, but that's probably a different feature of humanity, voluntary tax. All right. Okay, so this is a design parameter. And we're going to average over the spark probability, or pyromaniac probability. So if D equals 1 will be just random addition. You can do your testing, right? You've got your forest, it's half filled. You've got half of this big grid filled with trees. You randomly choose one of the open spaces, put a tree in it. You can test it, but you have nothing to compare it with, right? There's no design here. So that will be just random allocation of trees, which will be like percolation. You're just filling in things randomly. It'll feel like the percolation model. So the percolation model is a good thing to work on first, because there's no design in that whatsoever. That's this current assignment. And then this next piece, we lift it up a little bit. D equals n squared, then you test everything. This is still not the same as testing every possible configuration, because we're going to build out from like 0 trees, 1 tree, 2 trees, 3 trees, and it's going to be built on the best path that we got to 5 trees. We can't go back and test every possible thing. It's greedy. By an n squared, of course, as it fills in, there aren't, right? You lose places to put things. So this is kind of in quotes. It's like basically you test everything that's open. Yeah. All right. And so if the probability of a spark in each cell was 0, which could be, right? It's just like it's not a dangerous thing. Then you just fill it up with trees. Nature will do that. Of course, you get very weird things with evolution, right? So some trees seeds will come out when they're burnt, which is just weird. So Australia has those sorts of things. That's pretty fantastic. That's like really long-term stuff. It's good thinking by evolution. Oh, it doesn't work like that. But anyway, so every time you add something, you're going to measure the average area of the forest that's left untouched. Of course, when you start and you've only got, say, 3 trees out of this big space, maybe they're never burnt, right? They're going to get burnt now and then, rarely, and so on, but most of the time you keep what you have, but you didn't have a very big forest anyway. So we have to weight that, right? So we're going to be adding more and more trees. It's getting bigger and bigger. So we're going to potentially be able to preserve more and more of that, hopefully. And eventually, if we fill it up with all trees, right, eventually, I mean, at that limit, then absolutely every spark burns the whole thing down. So eventually you have to get to a point where every forest fire is n squared size, right? So when there are no trees, it's 0. When it's full of trees, everything burns every time because we'll always have a normalized distribution. Everything burns every time. So there's something that has to go up and down in some way, at least, right? Maybe it's got wobbles because it's weird, but you could imagine it has to go up and down. So we're going to have a distribution of fire sizes. So there's that. There's the average area, but there's also just what's the distribution. So given this configuration, let's light it up in all these ways, what's the distribution of fire sizes, right? Okay. And we'll talk about the yield as being the density. So it's the density of trees minus this average fire size. So this is this thing where I'm just sort of trying to talk about the limits. So at the limit of no trees, this is 0, and this is 0 because forest fire sizes are 0. There are no trees. At the limit of all trees, then this is a 1, and every forest fire is of size 1, or it's n squared. This is normalized by the thing. So it will always be, the yield will be 0, right? Nothing left. So this is what you started with. This is how much was burnt on average.